This n minus m plus r equals to 2. If G is a connected plane graph, then n minus m plus r equals to 2. It is always true for every connected plane graph. So this particular formula has been actually invented by Euler in the year of 1752. This is known as very famous Euler formula. Now the thing is, what is the importance of this formula in this context, that we need to know. So again, this n is the number of vertices, as we have already said, m is the number of edges and r is the number of faces. So let's prove it. First, let's prove this particular formula with the help of mathematical induction. We will start the mathematical induction on the number of faces r. So the base case r equals to 1, then G has no cycle. We have already seen if r equals to 1, then G has no cycle. Right? G is a connected acyclic graph. So it must be a tree, and we know that for tree, total number of edges is equals to total number of vertices minus 1. So in this case, m equals to n minus 1 and r equals to 1. So if we check that n minus m plus r, that is equals to, if we replace the value of m and r, then we get that n minus m plus r equals to 2. So for the base case, we have proved that Euler's formula is correct. Now, next, assume that r is greater than equals to 2 and that the result holds for all connected plane graph with r minus 1 faces. So this is our induction hypothesis. So we have already proved the base case. Now we have considered the induction hypothesis. What is that? We are assuming that the Euler's formula is true for all the graphs, connected plane graphs with r minus 1 faces. Assuming this, we will actually prove that if this assumption is true, then the Euler's formula is also true for the connected plane graph with r faces. Right? Let's start that. Let's G be a plane graph with r faces. Okay. Since r is greater or equals to 2, G will always contain a cycle. Okay. Now let's consider E be a cyclic edge. Then the graph G minus E is a connected plane graph. So we have this diagram, graph G. If you see, it's a cyclic it is a cycle. So I have marked the dotted portion. That means the graph is a very long graph. I have just marked few vertices and edges. Other thing I have not considered, but principally it is the same. So in this context, I have an edge E. That E edge is creating basically the cycle, right? So I can say that E is a cyclic edge. So now let's assume for this graph, the total number of vertices is n, the total number of edges is m, and the total number of faces is r. Okay. Now we will create another graph G minus E by deleting that particular cyclic edge from this graph G. So if we do that, so we have erased that edge E and we found that new graph G minus E. Now we should check what is the value of those three different n, m and r. Let's see that. So what is the value of n in this new graph? The number of vertex still remains same. The reason is E is a cyclic edge. If I delete the edge E, the graph is still connected. So there is no dangling, there is no isolated point. So there is no point of deleting any vertices. So the total number of vertices will still remain the same. So the total number of vertex is still n. Now what is the total number of edge? Since we have removed that edge e, so the total number of edge will be mg minus 1. So we have deleted one edge, and that is the reason actually the total number of edge is mg minus 1. Now the last point is r. We need to calculate the r for the new graph, right? And in the graph G we have two different regions, f1 and f2. Okay, so f1 and f2. So if we actually omit that e, then what will happen? We merge both of them and we create one, and we actually we create a single phase. So there is no longer there be a two phase. So the total number of phase also will be Rg minus 1. Now according to the induction hypothesis, if we see that since it is true for r minus 1 phases, so I have written that n g minus e minus m g minus e plus r g minus equals to 2, and I have put those values and I have found out that n minus m plus r equals to 2. So this is true for all cases. So the now finally we need to discuss a little bit about the consequence of Euler's formula. So we can always prove this inequality. It is pretty simple. We have already proved that twice m equals to summation of degree f, and what it is saying, the corollary is, if the simple graph such that degree f is greater or equals to k for every phase, then that inequality hold. Since the degree f is greater than equals to k for every phase, we can always write that the summation of degree f is greater than k into r. From there we will have r less than equals to 2m by k. If we replace this r in Euler's formula, we will get that inequalities. Now with the help of this inequality, we also can check whether k5 is planar or not. So we know that already k5 is not planar. We can actually revalidate the same. So for k5, the total number of vertex is 5 and total number of edge is 10, right? So now the value of k is equals to 3, because if you see the k5 graph, every phase will contain greater than equals to 3 phases. So k is equals to 3 here. So if you replace the value of k, then we will get that m should be less than equals to 9. So we have assumed that k5 is planar, and we have used that corollary, and we have found that m should be less than equal to 9. But actually we are seeing here m is equals to 10. So our assumption is wrong. So we can say that k5, whatever we have assumed k5 is planar, that is not true. Similarly, we can also say that k33 is also not planar. Initially we will assume that k33 is planar, and we will use the similar inequality. So in this case, since it's a bipartite graph, so in every bipartite graph, the value of k will be always greater the value of the phases will contain the total number of edge, which is phases will contain more than 4 edges, either 4 or greater than equal to 4 edges. So if I replace the value of k is 4 in the inequality, then we will get m is less than equals to 6, but that is a contradiction. So our assumption is wrong. Now, so what is the actually use of this particular Euler's formula? The use is very simple. So we have topologically we have proved that we can always prove that whether a graph is a planar or not using the Jordan corollary and other pigeonhole principle. But since Euler formula is applicable to the planar graph, so we can always, if the question is whether the graph is planar or not, first we will check n minus m plus r. If is equals to not equals to 2, then we can always say that this is not planar. Okay, but if the other way it is not true, if let's say for a graph we found that n minus m plus r equals to 2, we will not simply say that it's planar or not, because if the graph is planar, then we can say that n minus m plus r equals to 2. But if for any graph n minus m plus r equals to 2, we cannot guarantee that whether the graph is planar or not. So even before starting or doing the any algorithm or any topological way to saying that the graph is planar or not, first we check with the help of Euler's formula. That's the reason Euler's formula is very easy way to actually start with the problem. If Euler's formula say that if it is not equals to 2, then we can straightway say no, it's not planar. If it equals to 2, then we need to rethink or recheck whether it's a planar or not. So that's the art of Euler's formula. So that's all from this particular lecture of planar graph. Hope this will actually benefit the viewers, and for the detail you can go through any other standard books. So thank you again.